Welcome at Airborne. I'm Sander Woldendorp, the Director of Airborne Aerospace, and here at Airborne we make composite structures, so lightweight structures for high-end systems, like scientific telescopes, but also for satellites and launchers, things that go into space, or aircraft parts. Scientific telescopes has actually a long history in Airborne. With our customer CPI Vertex, we started many years ago on the development of a telescope which is now active on the South Pole. As a result of that, we developed the ALMA project together. Now, the next generation of telescopes has been developed and built with the SICAD and SOLAT. And this telescope will be able to look even further into the far universe. So it's pushing the boundaries of what is actually possible with doing astronomical measurements from Earth. At Airborne, we're really proud to be part of a program like this. And you also feel that my team is really honored and motivated to be part of such a technological development. I can remember that about 2-3 years ago there was the first picture of a black hole that was published. You know, then we start to realize that we're part of a big technological achievement. And that's really a good thing. Yeah.
So the big challenge with the design of this structure is that it has to be very stable. We need to make sure that the 6-meter mirrors do not deform. Actually, over 6 millimeter it may not deform more than 10 micrometers. So it requires a very stiff and stable structure because it will deform under its own mass. So the stiffness per mass has to be very high. And it may not deform when the ambient temperature changes. So to achieve that, we basically had to design our own material from the ground up. And we ended up with a hybrid carbon fiber structure where we used 2 different fibers to get the best of both worlds, of all worlds I should say, because it is very stiff, very light, it has a great thermal stability, and the costs are also still within check. And actually we designed a material which, when you heat it up, doesn't become bigger like all normal materials, but it becomes even slightly smaller. Another added complexity, if you compare it to, for instance, the ALMA telescope, is that this telescope doesn't have an axis-symmetric mirror. So in the case with, for instance, ALMA, if the temperature changes, the entire disk becomes bigger, but it actually becomes a bigger parabola of the same shape. And therefore it doesn't really matter for their focus point. But in the case of this mirror, it is not axis-symmetric, and thereby the issue basically changes from a 1.5 dimensional problem to a 3-dimensional problem, making it much more complex.